there are at least some of you in the audience who have heard versions of this talk before. So maybe there are some new things for everyone. Okay, and you can see here some of my collaborators. So I was telling before that Theo Nilsson is a former master's student of mine who is now in London and hopefully making a lot of money finance industry. Okay, so right, so Sasha asked about proofs. So now there will be some proofs, but unfortunately for small waves.
Then I will ask about computation.
Okay, so well, maybe it's not needed for this audience, but I wanted to explain a little bit what I mean by two and three-dimensional, so solitary waves. So by two-dimensional wave, I mean as usual that so the surface pattern is one-dimensional. There's basically no variation in this direction. And okay, so for these three-dimensional solitary waves, it's hard to come up with pictures, right? I've worked on it, know that. So, well, I mean, I don't know if there are better pictures than this at the moment, but these are some experiments by Duncan and collaborators, where so it's not really true solitary waves in some sense. I mean, there's some forcing by wind blowing on the surface, and you can see different things depending on how fast this thing is moving. Okay, but at least this has some similarities to the waves which I will show. Okay, so the idea is, right, so there's a lot of theory, of course, for two-dimensional solitary waves, going back to John Scott Russell, and then to Korteweg and de Vries, and so on. And so for three-dimensional waves, there is less theory, and there is some theory for model equations, like KP and nonlinear Schrödinger, etc. So what I want to talk about this talk is the corresponding theory for the full Euler equations, so irrotational Euler equations. So what can we say about small amplitude three-dimensional solitary waves? And I should explain also that, I mean, there are different kinds, for solitary waves in 3 dimensions, you can think of different kinds of solitary waves. So what I'm thinking about here are lumps or fully localized waves, which decay to the undisturbed state of the water in every horizontal direction. You could imagine something which decays in one direction and then is periodic in the other direction. Right, and this will mostly be a variational existence theory. I will not go very much into the proofs, but I will give you some ideas. And there are 2 different cases which I have to separate. So one is the strong surface tension case, where we get lumps looking something like this, and then weak surface tension, okay, something like this. And you can see this difference in the dispersion relation. We'll get to that. And also in the choice of model equations.
But how are these pictures obtained? What is plotted here?
Okay. So for this one there is for the KP wave there is so this is just basically the KP.
Both of them.
No. This is KP, and this is essentially what you get using the either nonlinear Schrödinger or Davis-Stewart's equation as a model. But this one is actually just a caricature, so it's just, I think it's made, I don't remember if I did, no, I think Mark Rose did this one. And it's probably just taking some, I don't know, Gaussian or something.
Your pictures are discussion with, but you're going also to talk about the elevation one? Or?
I just took one of them. So what Jean-Marc is asking about is important here. So there are 2 different branches of solutions here, one of elevation and one of depression. And in the theory, well, you will see. So in parts of the theory, we can't really tell which waves we are getting. And for deep water, we can actually say we get 2 different branches.
So how do you, I mean, what's the dividing line between strong and weak?
Okay, I'll get to that. Yeah. You're good at asking questions, which with the answer in the talk. Yeah. Okay. So, but there are also numerical computations of these waves by people in the audience, Jean-Marc and Amelia. Okay, so well, you know about this, but it's good to at least introduce the variables which I will use. So as I said, I will look at well, ideal flow and irrotational. So the velocity field is the gradient of velocity potential, which I will call phi. We have gravity, and in some parts of the talk we will have, so in most parts of the talk we will have surface tension. I will say something about what happens without surface tension, and you could consider also other surface effects, like so high, which would be interesting for the other program. You could consider hydroelastic waves that would work for some parts of the theory. And okay, so just to set the scene, I have x and z are the horizontal coordinates, and y is pointing upwards. And right, so we non-dimensionalize everything. Make the formulas a bit simpler. So gravity is now just 1, and the bottom is at -1. This will be at y equals 0. Okay. Right, so the equations of motion are Euler's equations, but yeah, so since I assume that we have irrotational flow, we just get Laplace's equation for the velocity potential. And then if we include, right, so the boundary conditions, we have the usual kinematic boundary conditions, and then the dynamic boundary condition, simplified using Bernoulli's law, looks like this. So now we have this surface tension term here. So in 3 dimensions or a 2-dimensional surface, it looks like that. You have the mean curvature of the surface. And beta then is the bond number, sometimes, well, or the inverse bond number, depending on your your preference. I'll just refer to this as the bond number. So it measures the effects of surface tension to, well, okay, so density, gravity, this is the depth. And this will be, so strong or weak will depend upon whether this is greater than or less than 1/3. All right, so, and as I said, we will be concentrating on solitary waves, moving in some horizontal direction, and there's no lack of generality in assuming that this is the x direction, because we have some rotation invariance. So c is the wave speed, and we assume that eta and the velocity field tend to 0 at spatial, well, horizontal infinity. Okay, so then in a moving frame of reference, the equations will look like this. Okay, so right, so before I go into the main part about what happens with surface tension, let me say something. Well, okay, so there you can motivate why we look at surface tension in different ways. But one is that, okay, so you can argue in different ways, either by looking at the dispersion relation or by referring to Walter-Craig. So there are some non-existent results for the pure gravity case. So if you have no surface tension, then Walter-Craig proved that there are no fully localized solitary waves with constant sign. So we all know that in 2D, gravity solitary waves are elevation.
One remark on side that this theorem was proven in the Isaac Newton's Institute for 1 week, during 1 week.
Okay.
So 8 of constant sign, you mean it's just no oscillations?
Yeah. Okay, so I think he just needs that it's elevation. I mean that it's below, above or below the asymptotic. I don't think there is a monotonicity.
Yeah.
I mean,
what does it mean? Fully localized?
Fully localized was just that it goes to 0 in every horizontal direction. Okay, so this of course still leaves the possibility of sign changing solutions. But, well, at least it's hard to see. I mean, if you from modeling, if you do some kind of small amplitude assumption, I mean, I look at the dispersion relation. It's not really. Well, I mean, there's no real proof, but as far as I know, that there are no solutions whatsoever. But I don't think so. Okay, so there's also, I'd like to mention that there is also another recent result by Miles Wheeler, still unpublished, but you can find it on arXiv. So this includes surface tension, but it's for infinite depth. So I mean, it could be with or without surface tension. So he actually proves some kind of an expansion for the waves, and so this is what the waves have to look at for at infinity, and then you can see from this leading order term that actually, so in 3 dimensions, then this will change sign of infinity. So I don't know of such of a rigorous result for finite depth. That would be interesting. Okay, so now let me go into the main part of the talk. So, well, to explain why we have these two different cases with strong or weak surface tension, you can look at the dispersion relation. So in 2 dimensions, it just looks like this. Right, so when we have strong surface tension, then we just get an increase in the speed is increasing as a function of the wave number, and for weak surface tension, we have this global minimum at some positive wave number, which I will refer to as K naught. So basically, yeah, okay, so in 3D, what happens is that you should just think of this as, so then you have 2 different wave numbers, K1 and K2 in the different directions, and what happens is just that it will be sort of increase, we will have a global minimum here, also in that direction. And the same over here, so it will just increase in that direction. Okay. Yeah, so basically, as I said, I will be talking about small amplitude waves, and then you expect to find such waves bifurcating near minima of these dispersion curves. So this somehow has to do with, if you look at the linear part of the equation, then you want this to be, you want to get some sort of elliptic invertible operator, but which is close to being singular. And so, I mean, you will choose, so what will appear in the linear part is basically this, but minus the wave speed. We will take the wave speed close to these minima and try to find solutions. Okay, so yeah, so the dispersion relations look differently depending on the size of beta and also the model equations that you get. So in this case, you somehow, so what we expect is that in the frequency or in the wave number plane, the action will be somehow concentrated close to these wave numbers. This is kind of where interesting things are happening. So over here, and you expect to get some oscillations in the solutions. And over here, you don't expect to see such oscillations because things will be concentrated near the origin in the frequency space. So for beta less than 1/3, you get these kind of modulated solitary waves. And the model equation in finite depth is the Davis-Stewartson equation. So now I've just written it in the stationary case, or steady case. So it looks like this. You can write it as a system. So you can think of it as a generalization of the nonlinear Schrödinger equation, where you have this extra term, like so. And then so you get a system instead. So this somehow takes care of mean flow effects. And you can also write it as a single equation. The price that you pay is that it's no longer a local, it's no longer a PD. So you have this non-local operator which appears here. So this just comes from solving this equation. Okay. Now, yeah. So the corresponding solutions will look something like this. So the way that theta and eta are related is through this formula where epsilon is a small parameter, so it basically is related to the difference between the wave speed and the minimum of the dispersion relation. Okay, so you see that you have this kind of oscillations that I talked about. And I said that we are looking for a variational theory, and so it's then interesting to know that there is a variational existence result for these waves. So yeah, I mean, the existence theory for the Davis-Jordan equation is not, there's no exact formula for the solution, but you can prove the existence using a variational principle. So critical points of this functional correspond to solitary waves, and Tripolati proved that this indeed has some critical points. Yeah.
There must be reduction to the integrable Davis-Jordan equation when the length goes to 0 or something.
Yes, but okay, so this is the there is an integrable
So
version
my
of this,
question-
so it depends upon the parameters.
And my question is the exact solution of this integrable equation which will be represented by
No, not so that, as far as I know, it doesn't have solutions which represent long solution. There are some other solutions. It's kind of long solutions. Okay, and then for strong surface tension, we instead have, so then we already heard about the Kp equation. I just called Kp to be on the safe side. So which looks like it has this interesting form. And then now it actually is integrable. Right, and then again there is a relationship between eta and zeta, which looks like this. Again, epsilon is related to how far away you are from the minimum of the minimum wave speed. And now there are explicit solitary waves, which look like this. Hopefully, I'm not sure if these constants correspond to these constants. Hopefully there is some resemblance. Okay. And again, now I have to be careful with what I say. There is a variational principle which gives you the existence of a solution. So I wrote it like this. So this is on, of course you could write this, I wrote it on the Fourier side, but you could of course write it also on the sort of physical side, but then you would have to take sort of the dx to the power minus 2. This is a bit complicated. It's not a very nice formula. So you can see it's somehow related to inverting this over here. Now, I have to be careful because there's no uniqueness result for the solution. So it's not clear how sort of the ground state solution that you get from this variational principle is related to this one. But I guess most people believe that what you get from the ground state variational principle is actually the solution. Okay, so now let's return to the water wave problem. So if we're looking for a variational existence result, we should have some variational principle for solitary waves, and of course there is. So you can either start with Luke's variational principle, or you're just using Sakharov's Hamiltonian formulation. So this is basically the energy. And now, what's bad about this formulation is that now phi is somehow defined in an unknown domain, so it's related to eta through the domain, and this is not very nice. So then there is this very nice trick of instead looking at the restriction of phi to the surface and expressing this integral, this Dirichlet integral, using the Dirichlet-Neumann instead. So phi is now just a function of two variables, big phi. Right, so this is that, and g of eta is the Dirichlet-Neumann operator. So you solve the Laplace equation with homogeneous Neumann data on the bottom, and then you have big phi as the Dirichlet data on the surface, and then this operator returns the Neumann data on the surface, and it's convenient to normalize it by this factor, so to get a nice formula. Okay, so now of course, I'm hiding some things here in the sense that, okay, so you get a nice problem here. I mean, the unknown functions that you're looking for are defined on known domains, but of course you're somehow hiding all the problems into this operator instead, so you have to understand this Okay, and I will not go into details about this operator in this talk. And I'll just say that everything can be worked on. Okay, but okay, so one price you have to pay is that, of course, that this is a non-local operator. It's important. Right, and then there is, so the energy is conserved quantity, and if you look at the time-dependent problem, and there is also another one corresponding to conservation of total horizontal momentum, things like that, or impulse, depending upon who you ask. And then solitary waves are critical points of this difference, so h minus ci. I mean, you could look at this in various ways. You could fix I and then look for constrained critical points, but here we will fix the wave speed and look for critical points of this function. Okay, so some difficulties. I mean, it's not easy to directly treat this variational problem. So first of all, it's not a semi-linear problem. It's more of a quasi-linear nature in the sense that, okay, so if you look at the highest derivatives in these functionals, they don't appear quadratically. Okay, so you can rewrite this. Okay, so I mean, so you have problems with coercivity. So I mean, somehow this appears quadratically, the gradient of eta squared, if you already have some control of the L infinity norm. You don't get that from the function. And it's not a finite sum of homogeneous parts, so it's not, as we saw in the previous talk, because it's Babenko, where you got very nice non-linearities, but here it's an S. It's non-local, as I said. We have an unbounded domain. Okay, so for these reasons, it's not so easy to do something using sort of the direct methods of the calculus of variations. Instead, what we will do is to try to use a variational reduction and to get a variational function which is close to what you get from the model equations. One other problem then, if you want to do this, is that we now have two unknowns in the others we have kind of one unknowns. But this is not a very serious problem, so I'll start by showing you how you reduce to just one unknown. Okay, so I'll do most of this for the case of weak surface tension, and then I'll tell you a little bit about what modifications are needed for strong surface tension. Okay, so as I said, we work with a fixed wave speed, right? But we have this parameter epsilon. So in the variational problem, C will not vary, will be given, but I will use the freedom to vary epsilon later. Okay, and we fix the wave speed close to the minimum of the dispersion relation, and it should be below, so that as I said, so that the linear operator is sort of invertible, but just barely. Okay, and so we first get rid of one of the variables, big phi. So we do this by fixing eta and then looking at critical points of this functional. And yeah, okay, so big phi just appears kind of quadratically in the problem, so it's not very difficult to solve this variational problem. There is a unique solution. So you can relate phi, so now we think of phi as a function of eta, and the relation looks like this. Of course, you have to invert t here, and there are some technical details here, but we'll not go into that. Okay, and now you plug this function into this functional, and you get a new functional which I call j. So the variational reduction works by saying that this critical points of this new functional, given that phi, well, give you critical points of the original function if you set phi like this. Okay, and here k and l are these two operators. So you recognize this from before, and this has now been changed. Okay, so this is now the functional one that we want to look at. And we somehow want to reduce this functional to a perturbation of the Davis-Stewartson functional, which Chip allowed to work with.
Erik,
Yes?
is there a unique point for every eta, or it is a result for eta to be small enough?
For this, right, okay. No, we don't need eta to be very small. It's essentially for
in the final.
I mean, yes, you need something for this to be well defined. Essentially, as long if you're just careful about how you analyze this, then as long as you sort of the surface does not intersect the bottom, there is no.
Because you could play with the epsilon as a small parameter, right?
No. I mean, just for this part, there is no. You don't really need that. But it will be important later. Okay, so now comes another, then there is a second variation of reduction. So, so remember that I said that most of the action is close to this wave number k0. So we do a reduction or a splitting, rather in Fourier space based on this principle. So we introduce two sets. So somehow we want to localize the frequency space near these wave numbers. And so chi is the characteristic function of these two sets. And eta 1 is just sort of the spectral projection onto this set, and eta 2 is then the remainder. So the idea is somehow that eta 1 should be the leading order term. And we later on want to sort of expand. Somehow we want to introduce the epsilon in the eta 1 and want to make some kind of scaling, but it's not so easy to do it directly in eta. We need to do this decomposition first. Okay, and then so the idea, what I said about the action can be seen as follows. So we can split the Euler-Lagrange equation in the same way. And it turns out that because most of the action is close to here, this part is actually easy to handle in the sense that the linear part of this equation can be inverted without any problems. So for that reason, we can solve the second equation for eta 2, and so we get eta 2 as a function of eta 1. Then again, we plug that into J, and we get the new function again, J2. Okay, and this is the final reduction. So there will not be another variation of reduction. So now for eta 1, we can do, as I said, we can do this, introduce this parameter epsilon in here and do a scaling. So it's not so easy to do it for eta. If you do it directly for eta, it's not so easy to just write it like this in a sort of unique way. It's not clear how things are defined. Okay, and so then we show that then we expand everything in terms of epsilon, and we show that a rescaled version of J tilde is equal to the Davis-Stewartson functional plus some small remainder. So this first part is exactly the Davis-Stewartson function. And so now this is somehow semi-linear enough so that we can prove the existence of critical points for this function. And this is just a small perturbation term. Okay, and we study actually, so one nice thing, well, depending on how you look at it, we don't study this function, so this is a kind of technical remark. We don't study it on the space H1, we actually study it on functions with compact spectra. It's a little bit special. Right, and so if epsilon is equal to 0, as I said, that we get the Davis-Stewartson function. So now there are different ways you could work on this. You could either use a mountain pass technique. So what we do is to use what's called the natural constraint set or Nahari manifold. So you see this is still not, I mean, it's not the recursive function. You cannot just minimize this. But what we do is that we introduced a sort of natural constraint. So if we had a solution, then the gradient of t would be 0, and especially it would be 0 in the direction zeta. So we introduce this as an artificial constraint. And when we do that, we get the function which is coercive. So some properties of this set is that, so you see somehow that's related to mountain pass. I mean, so if you look at the rays for the origin, then they will intersect this set in its most one point. For epsilon equal to 0, every ray will intersect in one point, but it's slightly technical for when epsilon is positive. And yeah, so this function has a strict maximum along the ray at the point where it reaches t. So this is kind of, see that it comes from kind of this constraint. You get that the derivative has to be 0. Okay. So you kind of already said that the derivative is 0 in one direction, and just look for the derivative in the other directions. And zeta is a non-zero critical point, if and only if it is a critical point of T restricted to this Nonlinear manifold. And now, so the nice thing is that T is bounded from below and coercive on the Nonlinear manifold. So from that we can get an existence result. Now there are some things, some technical things which I have hidden away here. So this term is actually a little bit difficult to deal with because it's still non-local, and we're working on the whole space, so we have problems with compactness, right? So we have to use concentration compactness. And then because of this being non-local, it's not so easy to deal with that. So the way we deal with that is to actually go back to the original Euler equations, where everything is local. And so therefore we don't, I mean, that's the way we deal with this problem with non-locality. I hope that meant something to someone in the audience. Okay, so then the main result for this problem is that there is a minimizer for each small epsilon, and this corresponds to a non-trivial solitary order wave. But just from this, we cannot really say much about what the wave looks like. Now going to deep water instead. So I'll explain what I mean by that in a minute, but you could also think of infinite depth. So there we can actually say more using a slightly different method. So we still do a reduction, but instead of using then a variational existence proof in the end, what we do is just use an argument based on the implicit function theorem. So one way, you can think of infinite depth, or you could take beta to be sufficiently small. So remember, in beta, the depth appears in the denominator. So that's why somehow if you think of small beta, you can think of it as large depth. So then we can actually say, as John Mark was asking about, that there are two branches of solitary waves. And we can say something about what they look like. So they look sort of to the leading order-like solutions of the Davis-Johnson equation. Yeah, and so, as I said, this also works in infinite depth, and it relies on non-degeneracy for ground states of 2D NLS. So by non-degeneracy, I mean that if you linearize, so if you take the 2D NLS equation, and you know that there is a radial ground state solution, so it's monotone has one side and so on. Then, okay, so if you linearize, then you will find some elements of the kernel, so you cannot apply the implicit function theorem directly, but what you find in the kernel comes from the sort of obvious translation symmetries of the problem. So if you restrict to functions which are symmetric in the x and z direction, then you will eliminate right, so this is for the NLS equation, and you can also get results for small beta because the Davis-Johnson reduces to NLS in the limit of infinite depth. Okay. Right, so let me say something about previous results as well. So there are, as I said, there are some a lot of numerical results, and by members of the audience, both for finite depth and for infinite depth. And then there are also, so I just talked about sort of steady waves, but you can also look at dynamics. I think most of this has been done for model equations. Perhaps there are some, I don't know if there are now some studies also.
Some was already some for the early also. Yeah.
So there are lots of interesting things that you can say about stability properties. Unfortunately, for small amplitudes, I mean, so the waves I'm talking about here, they're all unstable. But if you go to higher amplitudes, then some appear to be stable.
Was the depression was stable?
not for small amplitude, right? Or I mean, if you take very small amplitude. If you go higher up to higher amplitudes, I think.
For the elevation one, yeah. But the depression, I think, is.
I think there's some paper with formulation for model equations which say that for the small amplitude is unstable and is stable for higher amplitude.
Yeah.
But I don't think there is stuff for the full.
No. Okay. So maybe it's still.
Maybe maybe not for the. Yeah.
Right. So this method, of course, says nothing about stability. It's just a pure existence result. Okay. So yeah, before I go on to strong surface tension, let me say something about excited states. So this is for if you look at 2D NLS. Okay. So by 2D NLS, by the way, I mean the elliptic version. I should have said that before. So it has actually. So there is this ground state solution. So it's a radial solution, which is monotone and one sign. But there are also infinitely many other radial solitary standing waves, which, I mean, one for each number of zeros. And now you could ask, well, can we find something similar to these?
It's only one oscillation we see.
Yeah. Okay. So this is in a radial direction, and then just.
Yeah. No, my question is it going oscillating but going down exponentially fast? So we see only one.
Yeah, it's monotone. This is monotone.
No, but the one.
What's the tail doing?
What's the tail doing? Is it oscillating?
It does not oscillate.
Okay, it goes.
But this is just the envelope, I suppose.
Yeah, this is just the envelope. Yeah, so that maybe answers your question. This is just the envelope, not. Then you have to sort of multiply by some cosine. Right, so I show you a picture. I think I have something. Yeah, okay, so this is from a model equation which was studied by Wang and Milevsky, and so you have these these oscillations, and imposed on them you also have the sort of modulation oscillations. So, but you could ask, are there solutions to the full Euler equations corresponding to these solutions? And this again would rely. So, if you're in infinite depth or deep water, this would rely on having some kind of non-trivial RC. So I had my master's students investigating this. Of course, you can somehow guess that it should be okay because they have been computed. So, but I wanted to double check that this is the case. And indeed, I mean, there is no reason for why they should be degenerate here. So and it looks like they are. Of course, he didn't investigate all of them. He investigated some. But it's just a numerical indication. It's not. I guess you could do something using interval arithmetic if you really wanted to. So we can expect to see solutions to the full Euler equations in infinite depth with small beta corresponding to these solutions. There are also further solutions to the 2D NLS which are not radial, but for those it's not so easy to say. Right, so let me say something about what happens with strong surface tension. So here there already are a couple of at least two different other variational existence results. So the nice thing is that we can kind of unify it now, and we can prove existence in almost exactly the same way as in the weak surface tension case. And we also get some further information which we didn't have before. So if you use this method, so then what you see somehow in the proof is the actual KP equation, whereas in other proofs you don't really get the KP equation. So this is somehow, two motivations for why there is a third existence result. So this is all work in progress. So now we take C close to the minimum of the dispersion relation, and now the minimum is 1, the conversation I did before. And again we split like this. But now, so I said that the action was close to the origin in Fourier space. So you could think that maybe we should take some kind of disk around the origin, but it turns out that this is the wrong choice. So instead, so this is something Mark worked on for a long while, and it turned out that this was the correct answer. This is the correct set of technique. And so you can ask why should we choose such a strange bow tie? So part of the reason is because of how sort of the dispersion relation looks like close to the origin. And we have this problems with you have some kind of singularities. You also see this in the KP equation. So if you expand the linear part of the Euler-Lagrange equation, so it looks like this, and then you can get exactly the KP, and you see here that you have exactly this quotient K2 over K1, and it also appears in the remainder. So somehow you need to control this remainder. If you want this to be small, you have to control this remainder, or this quotient K2 over K1. Then if you have a set like this, then this quotient will be bound. Okay, and now if you work through all the similar all the arguments again, then you get this perturbation of the KP function. And again, so we started this on the same set, but you have to work here a little bit to show that you get something that this MK someone gives you something which is cursive. Okay, right. But the conclusion is then the same, that you get an untrivial solitary wave. And again, there are some previous numerical results. And as I said, there are two other variational existence results for the full order equations. Right, so there's one, the original one was in ARMA from 2008 is, I would say, much more complicated. It uses LP spaces with P different from 2 and a lot of things like this, which here everything is just based on P equal to, Hilbert spaces. And yeah, in particular it uses sort of Fourier multiplier operators in these spaces, which is not so straightforward. Then there is another result with me, together with Mark Groves and Boris Buffon and Shuming Soon, which again is more complicated, but so it has the advantage that it also gives a kind of stability result. There we actually look at minimizing the energy subject to the constraint of fixed moment. Okay, and finally, let me say something about excited states here as well. And it's good to have Dimitri in the audience so he can correct me when I make errors. So the KP1 equation also has infinitely many solitary waves. So this is due to Perinovsky and Stepan Jans from 93. I already knew of the Russian.
It's your father.
No.
No, let's see.
Dimitri. I should have put the D. Okay, and right. So I think I first knew of this paper by actually last time I visited here. I know that I talked with Emilian about it. Yeah. So, but apparently Dimitri showed me that there is an English version as well. So I'm happy to find that. And these are actually here these figures come not from that paper but by a newer paper by Shuron and Shai. Okay, so there are all the solutions, and I think if I understood Dimitri correctly, in this paper they don't include all of these. There are further solutions than the ones they have in their paper. Right. And okay, so then you could ask for corresponding water waves. And as far as I understood, I think that there should be corresponding water waves. Okay, so based on numerical computations. So these solutions are actually degenerate. So you do get a large kernel for these solutions. And this comes from some symmetry in the KP equation. But as far as I understood, these modes all have some kind of antisymmetry, which implies that you can, again, if you restrict to functions which are even in x and z, then you should eliminate this kernel, and so it should be okay to apply the implicit function theorem. I don't know if this is correct, Dimitri. Okay.
We can talk about.
We can talk. Okay. So I hope this to be the case. It's an interesting mathematical question. Maybe I'm not sure. These are probably very far from stable, so maybe not so interesting from the physics point of view. And there is also a recent result, a mathematical result. So the investigation of the kernel here by Chiron and Scheik is numerical, but there is also an analytical study by Liu and Wei for the ground state solution using integrable systems methods. And, so they claim that this is non-degenerate. Okay, so that's all I have. Thank you for your attention.
So what you showed on the previous slide, these are branches of solutions which bifurcate from the, there's two one at the bottom.
These two?
Yeah, are they separate branches or?
So for the same parameters, for the same fixed speed, you can get more than one solution. In fact, infinitely many. They're all given by the second logarithmic derivative of a certain polynomial. And the first one is a polynomial of degree 2, the next one degree 6, the next one degree 12, and then there's a very nice formula.
And do they have given some sort of zero amplitude, or like if you change the speed,
Yeah.
so you move the speed to some critical value?
So they coexist for the same range of the speed parameters. Therefore, if the speed goes to 0, they all go.
Okay.
Oh, they can exist for
the different branches. Yeah.
Okay. So for the model equation, like Davis shows on the KP, there is a way to characterize solitary waves as a minimizer of the energy subject to Neharim.
Yeah.
There is also another characterization, minimum of energy for the fixed momentum. Is
Yes.
it known that the same minimizer, it is known that the two minimizers are the same.
No, I don't think there is any.
So in one paper you prove the result
Yeah,
for
no,
the
it-
fixed momentum,
yeah,
in
no,
the
no,
other
it-
paper for the entire manifold, and it's not clear if
No,
it's the same.
potentially they could be different, although I believe that they are the same.
When you compared different variational approach, in one approach you got stability.
Yeah.
And how do you derive stability results? By looking at the second variation?
No, I mean it's sort of more direct in the sense that it's because we did exactly what you said. I mean we minimize the energy subject to the constraint of fixed momentum, and yes, since these are conserved quantities, then
Yeah.
Further questions?
So you said that small amplitude solutions might be unstable, and then large amplitude might be stable, right?
yeah, this is
It's a bit strange, but why?
Yes,
Why?
contained in I don't know if there is a
Well, it is in 2D, for one-dimensional waves, you find that also.
Is that right?
Yeah, you move all the branch of elevation change.
But then in 2D, the depression waves are
Yeah, I was
for
mixing
small-
this.
for small
That's the result I was mixing.
Yeah,
this.
okay. So don't.
An elevation wave, they are unstable.
So
but then
yeah,
they
okay.
get
So
stable.
I have one explanation actually. So the one sort of justifications comes from the fact that so the Davis-Jurson or the NLS equation. I mean that you have this blow up instability. So actually, if you so this is somehow the problem. And then I don't know for larger amplitudes you can't really argue using that. So that this is not. Well, this at least does not give you instability.
But this is not an argument to get stability, right?
No. It just explains the instability,
Okay.
not why they get stable.
And do you expect really stability for larger amplitudes?
This is what is seen numerically, but
Okay.
I don't know.
Including the stable for large amplitudes. So include you see the exchange stability. And for 3D for model equation, it's the same,
Yeah.
but not for the fluid.
Yeah, it's not.
You see the change in the energy by the function of C has a minimum or maximum or something.
Yeah.
Where is this UN base paper published?
It's just an archive.
Okay. The rest of the discussion was also to the.
Yeah.
So thank you very much, everyone.